My name is Ella Cedarholm. Can you guys hear me okay in the back? Okay, great. My name is Ella Cedarholm. I'm a part of the Shipboard Science Support Group on the Atlantis with Woods Hole Oceanographic Institution. And I'm really excited to be here in person. This is my first RV Tech in person, and it's in my hometown. I grew up here, went to school, middle school, high school, and UNH is my alma mater, so it's very surreal being here with you right now presenting at RV Tech. So thank you for coming. I'm going to tell a story today about a fault that we had on our 681 fiber optic cable. Going to touch upon a couple of troubleshooting methods, and one specifically that worked for us. I'll go into further detail on that. But for those of you who haven't had the joy of working with a 681 cable, this is what the cross section looks like. So you have three layers of armor and three copper conductors. And then there are 6 total fiber optics. 2 of them are steelites, so they have a steel armor around them. That's these 2 guys. And the other 4 fiber optics are encased in what's called a K-tube. So it's a steel tube, and on this specific model, that tube is uninsulated. And that ultimately, I'm giving you the punchline early here, was the cause of the problem that we saw. So there are 2 different models. I'm gonna make this guy smaller. Okay, so we can see the whole slide. There are 2 different models of the 681 cable in the UNOS fleet. One of them, which is on most of the ships, it only has 3 fiber optics. Those are 3 steel lights. Whereas on Atlantis, we have this A309063, which has the K-tube circled in red. So 2 of these reels were delivered to the fleet in 2019. One of them went to the Atlantis, the other went to the deep submergence lab. And this cable is used primarily for ROV operations. So the deep submergence lab uses it for their 2-body operations with Jason and Medea. And on Atlantis, we could use it with any of the ROVs that come on board. But in this case, we were preparing it for use with the Alvin observation vehicle. So this vehicle is not used every time that we deploy Alvin, but it's on board for emergencies so that we can view something going on with Alvin. So in this past summer, we went to Alaska. We dove Alvin to 5,800 meters, which was the deepest that the sub had been since the recertification in 2022. It was also in Alaska, where there's a lot of fishing and a lot of ghost nets and fishing equipment lost at sea. So the chances that Alvin might encounter something in these deep waters or with fishing equipment was higher, and we really prioritized preparing the Alvin observation vehicle. So in that preparation, we did a health check of the cable, and we did a high potential voltage test, which is a common manufacturing test for electrical equipment. We used this dielectric withstand tester, which stresses the dielectric material, that insulation on the conductors, at the operating voltage of the manufacturer's voltage of the cable. So that's 2,800 volts for this cable. We short all of the other conductive material together, and you're measuring for a leakage current from that conductor to the other conductors. If there's any leakage, the tester will shut itself down, and if there's any problem with the dielectric material, this test can worsen that problem. So we found a problem while we were doing this test, and using a megger, we tested the resistance of the fault, which was across these 2 conductors adjacent to that uninsulated K-tube. So that fault kind of varied depending on the testing conditions between about 5 and 20 kilo ohms. And yeah, that's all for this slide. So when we have a fault, as you all might have seen in the email string that the RB Tech email string that Brandy started earlier this year, the first recommendation is a TDR. Like 6 people responded to that email. What you're looking for is a TDR. So the first thing we tried was a TDR. And we, the TDR sends a low voltage pulse down the cable. Any imperfections in the cable will create a reflection, and the timing and strength of that reflection informs the nature of the fault. This is pulled this from the manual. You can kind of see there's some different types of traces that mean different types of faults. But we didn't end up finding anything mid-span. So upon kind of looking further into this, the TDR is not really the right tool for a multi-stranded cable, or at least it's not designed for that. It's designed for a controlled impedance cable, like a coax or an Ethernet cable. And the user manual actually says that a TDR can only identify faults, or at least this specific model can only identify faults below 200 ohms.
Right.
So,
That's right.
Quite low. Yeah. So we were way above that in our like 10 kilo ohm fault. Next, we tried a OTDR, similar idea. It's optical time domain reflectometer. Instead of a voltage pulse, it's sending a high powered light pulse down the fiber optic. Again, timing and strength of the light returned informs where your breakage is. We were hoping that the damage, whatever damage had caused the fault that we were seeing, would have been represented, and maybe it also damaged the fiber optics. We'd see it there. This is actually a trace from that cable, and this you'll see the reflection came right around 10,000 meters, which was about the length of the cable. So this leads to the test that we used that actually ended up working. So this is a very simplified version of our circuit. You have the green conductor, the conductor counterclockwise of it, or counterclockwise and clockwise. So the fault was across the green and the counterclockwise conductor. And the resistance of the full conductor was 47 ohms. So using this standard from the data sheet, we can calculate 4.9 ohms per kilometer is 9.6 kilometers for the full length of the cable. So if we can figure out what the resistance is of the cable on either side of that fault, we can use this to calculate the distance to the fault. So if we treat I've simplified this already simplified drawing even more, just down to one of the conductors included in the fault. We call the two resistances R1 and R2, and we treat this like a voltage divider or potentiometer. So this is the equation over here: V out equals V in times R1 over R1 plus R2. Stick with me here, gonna go through some math. So we attached a power supply to one of the bad conductors and sent 1 amp current through the conductor. 1 amp made all the math a lot easier. The resistance of the whole cable was 47 ohms, so our power supply charged at 47 volts. Then to get our V out, we measured the conductor adjacent to it, included in the fault, with our multimeter. On the wet end first, we got 31 volts, which with 1 amp is 31 ohms. We measured the dry end and got 14 volts. and for a total of 45 volts. So right away, with our simplified math here, you can tell that the fault was about 2/3 into the cable reel. It was pretty deep, not an ideal situation. And we had some error there, right? The 31 plus 14 adds to 45. That's not quite 47. So we had a 400-meter range where we knew the fault was. And as it turned out, there were actually two faults. One of those conductors, like I didn't show the K-tube here, but one of the conductors was faulted to the K-tube in a different place than the other was. But it's worth talking about other sources of error with this test method. Man, it's kind of does anyone have any idea of how we could get rid of this?
You can drag it to the top.
Just drag it. Like green. The arrow on the green?
Yeah.
This one. Oh, and then drag it from there? Aha, thank you. Okay. So I lied to you before. This is a more realistic version of our circuit. I've included the resistance, the internal resistance of our measuring device. So this is the multimeter. It's got an internal resistance of 10 mega ohms. And we actually have two voltage dividers here. So this is our first equation, and we have actually what we're measuring is not the real V out. Our measured voltage is being influenced by the resistance of both the voltmeter and the fault. So if we substitute those resistances in, we're basically multiplying our real value that we're looking for by 0.999. So the error here doesn't matter when you have a fault of 10 kilo ohms or 0.01 mega ohms. But what if, what if our fault was the same resistance as our measuring device? Well, then you would have 10 plus 10, or over 10 plus 10, 10 over 20. You'd be multiplying the measurement you care about to calculate your distance by 0.5. You'd have 50% error. So you're limited here to really one order of magnitude less than your measuring device. With that, you get 9% error, which is like 900 meters, and still pretty far off if you're trying to cut a cable and save as much of it as you can. That's what we did. We came back into port and we cut the cable mid-span. So this is us at the Scripps Pier. We spooled off 6.5 kilometers of cable. We remeasured it and narrowed in, and we found that, okay, now only one of the conductors was included in the fault. That's how we knew that there were two different faults. So we narrowed in on that last kind of 200 meters, cut the cable a second time, tested it with a measure to make sure that all the insulation was good. And we forklifted it out of the way to get ready for the next 3,000 meters. So we spooled on another drum, took all that cable off, and then we had to lead the end back onto the ship, spool on the 6.5 kilometers, and re-terminate both ends, the wet and the dry ends, mechanical, electrical, and fiber optic terminations. So I'm not going to steal Lance's thunder. He's going to go deep into fiber optic terminations with you, but yeah, you might remember back to my earlier slide of like the purpose of why we were doing this. We were going to 6,800 meter or 5,800 meters. So we had 6,500 meters of cable on the drum, which like fortunately was just enough. So with that, I just wanted to thank some people who helped me with this. I didn't come up with this test result myself. I'm not an electrical engineer. I leaned heavily on the expertise of Rick Stanger from the Alvin group, Chris Taylor from the Jason group, Marshall Swartz, who's our like SSSG wire guru. I'm sure you've heard that name before. And then of course, my colleagues, Katie, Chris, and Anna, who were there for all of the spooling and testing of the wire, and Tom Brown from Scripps, who helped us all the spooling. So with that, I'll take any questions, and then we'll move on to Lance.